Well, good morning, everyone. Welcome to ICCP 2024. So it's my greatest pleasure to actually welcome you for the first time to ICCP in continental Europe. And of course, you know, we chose Switzerland because it's really in the middle of continental Europe and on the, gorgeous Lake Geneva. So I would like to welcome you. My name is Sabine Süsstrunk. I'm the general chair of this conference, and I'd like to warmly welcome you also on behalf of the program chairs, which are Ashok, I apologize already for my pronunciations, Vera Garvavan, Rourke Horstmeyer, and Wolfgang Heydrich, who you will see in a minute. Now, we have, of course, could not put such a conference together without an absolutely wonderful organizing team. So I really want to acknowledge all of them by name. So the publication chairs were Vivek Bominathan and Akshat Dev, the finance chair Shuren Jayasuriya and Chinmay Ye. The website chairs are Dongqing Wang and Yufan Ren. The industry chairs are Eduardo Charbon and Feng Yang. The poster and demo chairs are Kristina Monakova, Aditya Bediredla, and Eric Bezam. The local arrangement chairs are Rafael Achtu and Nicoletta Isaac. And the PAMI chairs are Boshin Shi and Chenshin Dai. The DIA and outreach chairs are Emma Alexander and John Murray Bruce. And the social media chair are Martin Everett. So I think they all deserve a big round of applause. Now, the one person who really also has his own round of applause is Rafael Achtu. So Rafael is the local chair who has basically done nothing else in organizing this conference for the last few weeks. And he has done a tremendous job, and if everything goes right, and everything will, it's thanks to him, not thanks to me. So. Then we have quite a number of volunteers. These are PhD and postdocs from EPFL, and you can actually recognize them by the wonderful T-shirts they're wearing. And they are here to really help you out. So if you have any questions, any concerns, just grab one of them, and we try to solve whatever problem you're having. We have one photographer in the back. He's going to take pictures. They will be on the website. And we'll also basically are just around to help you. Also for them, I think, a wonderful round of applause. So thank you. Now, to make all of this possible, we have a number of sponsors who generously contributed to this conference. So our platinum sponsors are Sony and Huawei. Our silver sponsors are Rightly Robotics, Novavis, Pi Imaging, and Google. And our bronze sponsors are Omron, Kitware, Ubixept, Snap, and Qualcomm. And please, during the poster and demo sessions, don't forget to actually stop by their booth and see what they're actually doing. So many of them have come with a demo. So also for those as sponsors, I would actually ask for a round of applause. And you will certainly actually appreciate the generosity tomorrow during the dinner at the Olympic Museum in Lausanne, just as a teaser. So we also had, like last year, so previous years, we had student travel support. We had a very generous support from the US National Science Foundation, which enabled 10 US-based students to attend. And we had an equivalent generous amount also from the Swiss National Science Foundation, which financed for Asian-based students and for EU-based students. And this has been a continuous kind of opportunity for students to come and travel and present, and I think that is an absolutely great initiative. And I welcome all those students who came with these grants here to ICCP in Lausanne. And by far, last But absolutely not least, we of course also thank the IEEE and the IEEE Computer Society for basically sponsoring this conference. So a few numbers. Paper submission over the years, we were more or less exactly at the same spot than in previous years. We had 48 submissions, and we have 18 accepted papers, a bit more than about the program by Wolfgang in a few minutes. Now the sponsorship over the years, again, we are very lucky to actually acquire about $45,000 in sponsorship money. The ICCP posters and demos over the years were a little less. And I have to say that we had a little bit of a challenge in Europe, which I underestimated. It really is vacation time. And if anything, the Europeans take their vacation very seriously. So, you know, it's either in July they're gone or in August they're gone. So the north, you know, up from Switzerland north, they're all gone in July. And from, you know, France and south, it's all gone in August. So we couldn't win, right? So, but I think we're doing very well with 67 demos and posters. And so there's also 11 posters actually from papers. So you get, you know, you get to have the oral and then also the poster submission. Attendance over the years, we have 135 registered attendees, and we also have 30 EPFL, PhDs, and postdocs who you will see coming in and out. We made the registration for them for free so that they can actually come and profit from the opportunity. And in this case, you know, I'm kind of sorry, but they don't get the food. So you are the batches, you will get the food, the other ones will not, but please make them welcome, you know, to our community. When you see them around, if somebody doesn't have a badge, doesn't mean that they are not part of our community. Now a little bit of where we are. I think you have found us, so you know where the SG building is. That's a little bit of an overview where the EPFL metro station is, if in case you came by different means. Also, the EPFL Caledon bus stop is going to be important in a minute, and I'll explain in a minute. And then you see in the background the Ushi neighborhood, where the Olympic Museum is, where we have the reception. The Vidi Beach, if you want to go swimming, it's going to be nice, starting about 2 or 3 hours, and the Lausanne City Center. Here is a few things of the EPFL campus, so the Swiss Tech Hotel and the Starling Hotel, where some of you are staying. Then the EPFL Pavilion, which unfortunately right now does not have an exhibit, I think. I'm not sure if it's closed. The EPFL Innovation Park. The Rolex Learning Center, which now has exhibits. This is this wavy building you might have seen, exhibits the master project of architecture. And then there is Migros and Denner, that's a couple grocery stores right there on campus if you need anything, you know, it's a 5-minute walk from here. So here is the SG building where we're at, and here is the plan. So we are right now on the first floor. So this is the SG1 auditorium. Then the poster and demos are going to be on SG2. So you can then either go out by this back door or take the stairs outside. Registration desk you've actually have found, and then the lunch, coffee, and sponsorship demo booths are downstairs on the ground floor. And also the Industry Consortium room, that's the lunch tomorrow, for those of you who signed up, will be downstairs in the corner. So lunch, coffee, always downstairs, then the talks will be here, and the poster demos at the top. The registration desk will be manned continuously, so if you need anything, please do not hesitate to go to the registration desk. Tonight we have a community drink, and that is actually also on the ground floor. You go this way out to the terrace, and you will find it. Now, something that's sometimes also useful are the bathrooms. So There are actually bathrooms, if you go through these doors, these glass doors on both ends, they're not locked. And then look for the sign WC. So it's not called toilets, it's WC in France. So when you see WC, that's actually your bathroom. WC. Now the internet is, I think, not working. Exactly. So for all of those in academia, you probably have EduRoam. We're trying to work this out. It should be working relatively soon. But it would be, the network would be ICCP2024, and then a username and a password. You also have the same thing on your program. It's written on the program on the last page, or on the third page, sorry, next to the barcodes. So when it's working, and we'll let you know, then you can actually use those words. Now to the program overview. So today we have our first keynote by Davide. Then we have 7 orals, 3 invited talks, and the first poster and demo session. We have the lunch and the women's lunch. And then we have the evening cocktail events, this community drink, as we call it. We also have from 5:30 to 6:30 this outreach event, but we'll give you some more information about that this afternoon. Tomorrow, we have a second keynote, 8 orals, 3 invited talks, and a second poster and demo session. And what's not mentioned here, tomorrow, just before the lunch break, we'll have the group photo right outside here on the hallway, and we'll take the photo from the other side, and it's actually a nice visual. So don't run out before lunch before having your picture taken. So that's going to be tomorrow before lunch. And then over lunch, you also have the Industrial Consortium. You also will get more information about that tomorrow morning. In the evening is going to be the reception at the Olympic Museum. Wednesday is the third keynote, 3 orals, 2 invited talks, and then the prizes or the awards. That is going to be given in the closing ceremony. You will get lunch on Wednesday if you choose to stay, and then it's going to be the end of the conference after lunch. So our 3 absolutely wonderful keynote speakers are Davide Scaramuzza from the University of Zurich today, then Yannick Roland from the Rochester University tomorrow, and Sylvain Chigon from INS-CNRS on Wednesday. We also have a great lineup of invited speakers. Amir Samir today from EPFL, Luat Wang from UC Riverside, Emma Alexander from Northwestern University, Ivo Irka from Siegen University, Fei Xia from ENS Paris, Chiamin Wu from Tsinghua University, and Alexander Alayi from EPFL, and Mark Scheinen from the Weizmann Institute of Science. The colors mean which day they will be speaking. So blue is today, orange is tomorrow, and green is Wednesday. Warning, Emma, with all the mess of the flights for Friday, you know, the security updates, you know, these people would rather be working in imaging, or aren't we glad they're not working in imaging? It's a bit of a mess, especially from the US, right? And so Emma could not make it. So, you know, exceptionally her talk will be shown by Zoom. She will give her talk, but it has to be by Zoom. So, you know, there's other people, even in Europe, it's still kind of percolating through who could not make it, and that is just a shame. Now, ICCP has a YouTube channel. For the poster submitters had the choice of actually sending a 1-minute spotlight video. These will be shown just before the poster session this afternoon, but they are already online on this YouTube channel. So you can actually go, and you have the link at the bottom, you can actually go and see those already on it. Now, all the talks will be recorded, And we will put the talks online then on this channel after the conference. And so if you do want to then, go back to some talks or, refer other people to the talks, please feel free to do that. But it'll be a few weeks after the conference. And here I do want to also kind of say thank you to the AV team at EPFL, who basically for free is recording all this and does the editing later to basically so we have good talks that we can put on our site. Now, ICCP is also on social media, specifically Twitter, YouTube I just mentioned, and Facebook. Our social media chair is Martin Everett. He will post throughout the conference pictures and impressions, also taken by our photographer, Federico Stella, who's basically taking pictures. If you do not want to have your pictures taken, basically tell him when he does and say, go away. But I'm not gonna, I'm gonna kind of make it a little bit your responsibility if you don't want to be on any of the photos. Now, the posters and the demos. So we have 2 poster and demo sessions today from 4:30 to 6 and tomorrow from 4 and 5:30. And Christina and Eric will actually give you some introduction to those closer to the poster session. What we're asking you to do is you can set up the poster during the prior coffee break or actually anytime you want. If you want to keep your poster, please uninstall it. For specifically the ones today, please uninstall it before tomorrow's poster session. So at the coffee break before the poster session, we'll take off all the posters that are still there and recycle them. So if you want to keep them, please take it away. And the ones for tomorrow poster session, you can leave them up till Wednesday to the end of the conference, and then hopefully, take it away if you keep it, and otherwise we will just recycle them. There will be a Best Poster and Demo Award from a list of shortlisted poster, and you can be able to vote on those, and so stay tuned for the details on voting. Then the Industrial Consortium, I mentioned before, and I'm not going to go, it's going to be a Tuesday over lunch. I'm not going to say too much about it because Dacian will actually give you some introductory words tomorrow morning. Now, EPFL is trying to become as sustainable as possible. Talking about trying, right? It's always not that easy. However, we have actually more or less banned all one-way, food thingies from campus. So what's going to be in your lunchbox is basically recyclable material. It's not going to be soft, it's hard plastic. So bring everything back actually to the lunch desk, and the cafeteria will actually take it back and wash it. So it's not to throw away, please bring it back. Same thing a little bit with your water cups. So there are some water cups, but there are not too many of those. So we gave you a water bottle. There's 2 water fountains, one downstairs, one upstairs that we refill. And by the way, the water in Switzerland, the tap water is drinkable, right? So there's not a problem to fill it up anywhere. And if you want, because all the bottles do look the same, we have pens at the registration desk so you can put your name on the bottle. But we'll be, trying to keep the trash to a minimum and use most of the recyclables. And then, of course, we hope that you'll use that water bottle through the year and advertise ICCP of next year, right? So you're going to kind of post this everywhere and make nice advertising for future conferences. Well, this community drink, I already mentioned it. It's this event, cocktail event. It's not going to be dinner. So it's just, drinks, a little snacks. And then for your dinner, you're on your own. There are some restaurants here on campus. There's an Italian place and a burger place not too far. Otherwise, take metro number 1 into town until the metro number, 1. Flon, in this direction, Flon is the last stop. Get out, and there is a gazillion restaurants around. You all, if you're staying in a hotel, you all got a public transportation pass, so you don't have to worry about those. If you haven't checked in yet, you can check in later, but you get this public transportation pass, and you can get in any tram, metro, bus, whatever you want, for free. Keep in mind, though, it's just for Lausanne, it's not for any other kind of cities. Now, tomorrow we have the reception at the Olympic Museum. As you know, the Olympics are going to start in Paris in a few days. Is anyone going to go to Paris after this? Yeah? Okay, so we have a few. So we get you into the mood, because you might not know, but the Olympic headquarters are actually here in Lausanne. It's not at the same spot as the Olympic Museum. The Olympic Museum is another kind of place, and we're actually going to go to the Olympic Museum, and you can have a private visit. What this means, you can just basically walk through the museum starting at 6 p.m. Then we're having a drink on the terrace, and the terrace here actually means, like on this photo, the entrance just before the museum, starting at 7 p.m., and then the dinner is going to be at the restaurant on the top floor of the museum, with a gorgeous view actually over the whole lake at 8. But I'm asking you again, please wear your badges so the people there at the museum know who you are and that you belong actually to this group. Just wear your badges. Some of you have this dot for vegetarian or non-vegetarian. If you don't have a dot, that means you're eating everything. If you have a dot, then you actually indicated that you have some allergies or would like vegetarian or something. Just double check that you have the right badge. Now, it takes about half an hour to get there by public transportation. And there's a lot of options. So we can take the metro at the station right there, or we can take the bus number 1 and walk a bit. Google Maps does a pretty good job telling you how to get there and which public transportation to take. However, we have a lot of volunteers, and what we're going to do, just go more or less to the reception, and then as a group together, we go with a volunteer, and they will guide you to the Olympic Museum. And otherwise, you really cannot miss it. It is the Olympic Museum. Then, last but not least, we have, for the 3rd year in a row, the photography competition. So, we are the Computational Photography Conference, right? We have to have a photography competition. And so I'm extremely grateful for the people who actually invented this 2 years ago. So, take pictures, upload the best 3 of them you have by Tuesday evening, and then the community will vote on Wednesday morning. Now, what's going to happen is that, well, actually, let me just first show you the link. So you have the link on the website, but you can also have it on this QR code. Now, the winner gets bragging rights as being the best photographer at the Computational Photography Conference, and actually some nice little prize, which cost about $0. Now, I hate to do this because we hardly ever started, the conference, but I'll do it anyway. Now, last slide, looking into the future of ICCP2026. If anyone here is interested in hosting ICCP in 2 years, please talk to either Ashok, Wolfgang, or me during the conference, or write an email. Primarily, I think write an email to Vajak because his email is the easiest one to actually remember. So, talk to us now because next year is set. We will make an announcement in the closing ceremony about where it's going to be, but the one for 2026 is not yet set, and if you're interested in hosting it, do talk to us during the conference. And now I'd like to introduce you Wolfgang, who's going to give you some more details for the technical program.
Thank you, Sabine. All right, so I'm Wolfgang Heydrich, and I'm one of the co-chairs of the Technical Papers program. My other co-chairs are Ashok Veeraraghavan, who's sitting here, and then Rourke Horstmeyer, who unfortunately couldn't make it. And then we have actually also a PAMI chair, Boxin Shi, and I will talk about the PAMI in a second. But basically, we had 48 submissions, that's already been pointed out before. And of these, 18 papers were accepted total. So that will be the program that you will see in the next 2.5 days. Now, we have a long-standing, multi-year anyways, collaboration with transactions on pattern recognition and machine intelligence, which is one of the top-rated IEEE journals. And basically, we get to nominate some of the highest scoring papers from our program to be directly published in the PAMI proceedings. And the PAMI chair is basically an associate editor with the PAMI journal and is responsible for making that transition. There's just a little bit more checkboxes to tick along the way. But basically the electronic proceedings that you have access to contain both the conference-only papers as well as the PAMI papers, so we'll be able to see all that content. Now, after the conference papers will be available in separate proceedings from the PAMI, which is going to be a special issue of the transactions on pattern recognition and machine intelligence, pattern analysis and machine intelligence. Okay, so that's the high-level view. Let me tell a little bit more about our review process, because I think there's a very strong tradition at ICCP to have actually a very thorough, journal-like review process, even for the papers that are only conference accept. So if you're coming, from another community, maybe there are in other communities, maybe there are it's more common for conference papers to only have like an extended abstract submission or something like that. But that's not how this conference works. So what we actually have very thoroughly reviewed papers. So every paper had 3 to 4 reviews from the International Program Committee. There are actually, I was able to see, the reviews across the board, and I have to say I'm continuously impressed by the quality and the detail and the expertise of the reviewers. Actually, right up there with the best journals in terms of depth and expertise. So then these reviews come back, they're presented to the authors. The authors have 1 week to write a rebuttal and address some of the major concerns. And then, after those rebuttals are in, the committee members that were assigned to the papers, they actually reach a consensus decision. Well, I guess in some years it's not always a consensus possible, but in this year we actually did not have to step in on a single one of these decisions. So it was all consensus based among the PC members that was assigned to the papers. The one thing where we as chairs have to step in to make a final decision is the PAMI paper. So there's a recommendation from the committee members on each paper, but in the end there are some restrictions to the total number of PAMI papers. And so again, this year was easy because we just accepted everyone that was recommended as a PAMI paper, because we had enough, or the recommendations were in line with the budget or with the quota that we have. But that was our final decision. And then finally, that's not the end of it. All the acceptances at that stage are actually conditional to possible mandatory changes. And so there's actually a shepherding process to actually make sure that the final papers actually include those changes. So it's actually, you can see it's a very thorough process. And I think we have some really high quality papers as a result of that. Okay, so the proceedings, basically there is, I'll show you a QR code in a second. There's also been an email, so you should have that information already. You can download it, and afterwards the conference papers will be on Computer Society Digital Library. The PAMI special issue will be separate. Let me just show you the QR code, so in case you haven't seen the email. So that's a link to a PDF for the preliminary proceedings that contains both categories of papers, and it is password protected, so there is the password on the slide as well. Okay? Everybody have their shot? Okay, good. All right. So then, talking about awards, so there will be, in the closing session, there will be a number of awards that will be given. First one is Best Paper. We do have a separate committee, actually, that will decide on the Best Paper. So the individuals will be identified in the closing session, as well as the, obviously the result of the Best Paper. And then we have also a Best Poster and a Best Demo Award, and you'll hear about those at a later time. And then finally, of course, already mentioned the photographic competition, or the Best Photo Award. And I think the new rule as established last year is, if you want to be paper chair for this conference, you have to serve as a motif for the winning entry of this competition. I think this is the new rule now. Okay. All right. With this, thank you very much. And I will now hand it over to my co-chair, Ashok, who will actually introduce the first keynote speaker.
Thank you, Wolfgang. I'm just really, really delighted to be here today to invite Professor Davide Scaramuzza to give his keynote. Professor Davide Scaramuzza is a professor of robotics and perception at the University of Zurich. He did his PhD at ETH Zurich, a postdoc at the University of Pennsylvania, and was a visiting professor at Stanford University. His research focuses on autonomous and agile navigation of micro-drones using standard and event-based cameras. He has pioneered autonomous vision-based navigation of micro-drones, which inspired navigation algorithm of the NASA Mars helicopter and many other drone companies. In 2022, his team demonstrated that an AI-powered drone could outperform the world champions of drone racing, a result published in Nature and featured on the magazine cover. His result marks the first time an AI defeated a human in the physical world. His research contributed significantly to visual inertial state estimation, vision-based agile navigation of microdrones, and low-latency, robust perception with event cameras. He has won numerous technical awards. I can't list all of them here, but including a Kiyo Tomiyasu IEEE Technical Field Award, an IEEE Robotics and Automation Society Early Career Award, an ERC Council Consolidator Grant, and many, many paper awards. Without taking too much of your time, I would be delighted to welcome Professor Davide Scaramuzza.
Thank you.
Thank you.
Thanks a lot for the introduction and for inviting me here. It's really a pleasure and an honor to be speaking. It's the first time, actually, that I'm also attending this conference. And it's nice to be back at the EPFL. In fact, I started my PhD at the EPFL with Professor Roland Sigvart. Then he moved to ETH Zurich, and that's how, actually, I ended up in Zurich. So I'm a roboticist. I've been working on robotics, actually robotic vision, for 20 years. First, I focused on self-driving cars. And then in 2009, when Google announced the self-driving car project, I thought it was actually time to maybe look at a new type of robots, and so we decided to move to a third dimension, and then we started working on autonomous drones. That's exactly how it went, actually. But over the years, I started realizing that perception is limited by the sensor, and so today I'm going to talk about a camera that we have been very excited to work on, which is called an event camera. It's a new way of sensing. And I also brought two of my team members here, Manasi and Mark, who are in the second row, and we have also two posters to present you. Before I delve into the details of event cameras, maybe let me try to motivate it. Let me start by showing you video demonstrations of the recent accomplishments of the robotic community. This is a very famous company, Boston Dynamics. And they showed a few years ago that their humanoid robot called Atlas was able to perform parkour, which is a very difficult sport, even for us humans. And what were the key enablers of this? Well, actually, perception. Finally, they had a perception system that was robust enough to estimate the robot state, which means position and orientation, and also the joint angles of the arms, but also model predictive control, which is a class of control algorithms that allow you to predict the next footsteps in a receding horizon. And you can see the predictions on the green boxes. You see those footprints. It's basically where the robot, according to its models, predicts that it's going to land. And then it updates these predictions as soon as more information is gathered. But perception is not perfect, and we know that very well. It's sensitive to noise, changes of illumination, exposure control is very difficult, sometimes there are missing pixels, and so things can sometimes go significantly wrong. So here you see impressive, spectacular, actually, failure points of Boston Dynamics Atlas. So robotics is very, very expensive, also because for this type of tests, you spend a lot of money. Let me show you another video. This time it's from my lab. So as it was said during my introduction, last year we organized the first AI versus human drone race, where we outperformed the two world champions drone racing pilots. So you're going to see a footage of this event. The autonomous drone is colored in blue, and the best of the human pilots is in red. The drone, of course, won, otherwise I wouldn't be here telling you the story, with a lead time of 0.5 seconds. Is this a lot? Yes, it is, because in drone racing competitions played by humans, the difference between the first and the second winner is usually 0.1 seconds. In addition, the iDrone won the majority of the races, so 15 out of 25 races. What were the key enablers? Well, first of all, a perception system that relied on a neural network to detect the gates, so the doors where you have to pass through. By the way, in drone racing, you overfit the task, so you know the environment in advance, and then you practice for weeks before the race in order to try to give the best performance. And we used also PMP, the famous perspective endpoint algorithm, which is 40 years old, in order to triangulate the position of the drone. What about control? Unfortunately, optimal control, like the one used by Boston Dynamics, will not give you the best performance when you're pushing robots at the limits of physics. So we actually relied on a neural network controller trained with deep reinforcement learning in simulation. So these two were the key enablers of this. But again, let's look at the failure points. So humans crash, we also crash. But at the moment, we crash a lot because we also cannot generalize to environments that have not been seen at training time. So again, it's a problem of perception. At some point, the firefighters asked us to open the hangar doors, and all of a sudden, the drone could not even take off from the podium. Okay, so this is to tell you that perception is still very, very limited. That's the reason why we don't have autonomous cars, because we humans are just too good. We make an accident every 100 million kilometers. and no autonomous pilots is there yet. So with this, let me motivate why event cameras. So if you look at the past 6 years of research in computer vision, they have been dominated by standard cameras. But as we know, they suffer from motion blur, especially in low light, because you need to expose the image for a certain time. They also suffer from a low dynamic range. There are high dynamic range cameras. We are very expert in that as a community, but we know that you have to take multiple times with different exposure times, sacrificing latency. And talking about latency, standard cameras suffer from a bandwidth latency trade-off, which is actually the key limitation for safety in robotics. What do I mean by that? Well, typically, in robotics, you want to have a very low latency, so very fast update rates. How do you achieve that with a standard camera? You increase the frame rate. But what do you pay by increasing the frame rate? Well, you are going to increase the bandwidth. The bandwidth is proportional to the frame rate, or inversely proportional to the latency. So how do we handle that? Well, then you sacrifice then a little bit the latency in order to reduce the bandwidth. Do you know what the latency of the state-of-the-art advanced driver assistance systems like Tesla, Volvo, Volkswagen, BMW is? 33 milliseconds, 30 hertz. They use 30 hertz cameras. And actually, one image is not enough. To make informative decisions, they take 3 images. So in principle, the latency is 99 or 100 milliseconds. So when you choose a camera, typically you choose the resolution, then you have a parameter you can change, which is the bandwidth and the latency. So as I just said, if you want to have a low latency, you are going to sacrifice the bandwidth. If you want to reduce the bandwidth, you have to sacrifice latency. So whenever you pick a camera, you are bound to move on this hyperbola, the bandwidth latency trade-off. The hyperbola can shift depending on the type of camera resolution, but the behavior will not change. An event camera is a sensor that allows you to get off the curve. You can have an arbitrary latency at an arbitrary bandwidth. You can cap it. And we'll see how this is possible. So what is an event camera? Maybe let me ask you, how many of you have heard of event cameras before? That's great. How many have worked at least once with event cameras? OK, so let's say one quarter of you. So an event camera is a camera that measures only motion in the scene. And you see here what I mean. Here I'm moving my hand in front of the event camera. The dots are events. There is also some background noise, by the way. We will see what the color corresponds to. But if I move the camera with respect to the scene, then again, of course, there are events. As you can see, events do not spike on all pixels, but only in correspondence of edges. Why? Because in the end, how does the event camera detect motion? By checking for changes of intensity. And typically, changes of intensity happen to be on edges, right? So an event camera naturally responds to edges. Now, that's not it. These events are not triggered frame time at the frame resolution. They are triggered asynchronously. A microsecond resolution every time that a pixel detects a change of intensity. You see here what I mean. Let's assume that the visual stimuli is a rotating dot. So the standard camera would output frames at constant time intervals, while the event camera will output a spiral of events that corresponds only to those pixels that detected the change, so the motion of the dot. And what happens if I stop the disk? Well, no events are generated, so the bandwidth is 0, because there is no motion. So in principle, you have a drastic reduction in bandwidth. But what happens if I move the disk faster? The standard camera suffers from motion blur, and event camera does not, or at least it has negligible motion blur. What you must remember is that the information streamed by an event camera is continuous in time, okay? Continuous. It happens at 1 microsecond resolution. So these 4 are the 4 key advantages of an event camera. Low latency, low bandwidth, negligible motion blur, and very high dynamic range, of course, because it doesn't accumulate photons over time. So it resets every time that you pass a threshold. So we'll see. in a moment how it works. The problem, though, with event cameras is that you cannot directly apply traditional computer vision algorithms, but you need to adapt them in order to cope with the asynchronous nature of the sensor, okay? Many people ask me, who sells event cameras? So I decided to put a slide here. Actually, there are only 3 companies that sell event cameras. So historically, the first one is Innovation. It was founded by a professor in my department, Professor Toby Delbrook, and commercialized in 2014. They sell VGA resolution sensors. The cost is 5,000 francs, dollars. Then there is now a big company, Prophecy, which I would say at the moment is the largest. They are based in Paris, and they made the sensors for Sony. They reached, thanks to Sony's money, they reached the resolution of 1 megapixels, but the cost is still high. Innovation, meanwhile, has partnered with Samsung, so they're also selling the Samsung Innovation camera. And then there is another one based in China that was recently acquired by OmniVision, also 1 megapixel resolution, but much cheaper price. And many people ask me, when will we have cheap event cameras? Well, there are already, in fact, if you buy them as part of a product. For example, the product Samsung SmartThings Vision has an event camera here, and it costs $180. But the cost, in general, is expected to be low when a killer application is found. Think about time-of-flight cameras. They were invented in the 90s. The first time-of-flight camera was available to a few robotics labs, including my former advisor, Roland Sigvart. It would cost $20,000, and 20 years later, it cost $20, thanks to this iPhone 10. So the market can drive costs down. Let's go back to event cameras. Why are they called the bio-inspired sensors? Because they really mimic the working principle of the human eye. So we have cones and rods. Interestingly, we have, for each eye, 130 million photoreceptors. Let's call them pixels. But interestingly, we only have 2 million axons. Let's call them the wires that connect the pixels to the brain. So we have 60 times more photoreceptors than the amount of wires. How is this possible? Because our photoreceptors trigger information asynchronously. And then the ganglion cells, they multiplex. So whenever a photoreceptor receives some photons, actually 300 photons, that photoreceptor will trigger information to the brain asynchronously. So how does the event camera work? Now let's get into the details. I don't know if some of you have some electrical engineering background, but this is actually the schematic of a single pixel of an event camera. So the front end is the same as that of a standard camera, a photodiode. But then there is a capacitive divider that removes the DC component, so the absolute intensity. The event camera only measures the varying component of the visual signal. That's why when people ask me, can you imagine doing everything with an event camera? No. Just because it doesn't measure absolute intensity. So you need to pair it eventually with a standard camera. So we say that event cameras are complementary to standard cameras. After the capacitive divider, there is an operational amplifier that amplifies the signal, and then there are 2 sets of comparators. What do? They check whether the delta of intensity, so the difference of intensity since the previous event, passes a threshold. Okay, now let's try to repeat that by looking now at the intensity of a pixel. By the way, an event camera is sensitive to the logarithm of the intensity, but let's call it intensity for simplicity. This is the intensity of a pixel, 1 single pixel over time. An event is generated whenever the intensity difference at that pixel passes a threshold since the previous event. So let's look carefully. Who decides the threshold? You. You tune the threshold. Typically, this threshold can be tuned between 10% and 50% of the current intensity level. So it's a relative intensity level. You see, here, the delta of intensity was positive, so we record a non-event, positive event. What about now? Now, the delta of intensity since the previous intensity level is now negative. So we call it a negative event or off event. Off event, on, and so forth and so on. So as you can see from the x-axis, the generation of events is not uniform in time. It's asynchronous. It's event-driven. That's why they are called event-based cameras. Because whenever the pixel detects a change of intensity, that pixel will trigger information. Now, let me ask you a question. Can you reconstruct at least the relative intensity of the signal at any time? If you think yes, raise your hand. Not the absolute, the relative intensity. No more hands. Yes, of course you can, because you imagine that you know the initial intensity, which you don't know, but you can set it to 0, for example. Then you can just sum up or subtract the positive and negative events, and then you can reconstruct the intensity at any time, relative intensity, because you are doing integration, right? So you can integrate and reconstruct the signal up to an unknown bias. That's the rule of integration, of course. We have done it. Many people have done it. What you see on the left are raw events. What you see on the right is the reconstructed intensity of the image, up to an unknown scale factor, up to an unknown bias, sorry. But now, what is the cool thing about these reconstructed images from events is that they now inherit all the nice properties of event cameras. So in principle, they do not suffer from motion blur. They have a very high dynamic range. And you can render them at any temporal resolution. In practice, up to 10,000 hertz, because there is a cutoff frequency of the sensor, unless you inject more money to buy a better sensor. Let me show you a high-speed application of this image reconstruction that we did a few years ago. On the left, you're going to see what at that time was one of the best smartphone cameras, Huawei. And on the right, our reconstruction at over 5,000 FPS. Here, we are shooting a bullet with the gun at 1,300 kilometers per hour. You can see you can reconstruct the intensity at much higher temporal resolution. The temporal resolution is limited by the cutoff frequency of the sensor. Okay? Now they're building gigahertz event cameras, or even faster. This is very interesting. Our reconstruction is on the left, and the phone camera is on the right. You can see that you can actually have a very high dynamic range. So when you even exit or enter a tunnel, you are not subjected to this overexposure or underexposure of the sensor. So you can enable detection of pedestrian, bicycles, and cars at much higher dynamic ranges that you could possibly do with the standard cameras. But we are not interested in reconstructing the image, because otherwise, what is the point of using an event camera? You are actually then going to lower the latency, right? So how do we apply now event cameras to computer vision without reconstructing the image? So going directly from events to the output of your ideal computer vision algorithm. So let me start from the basics. Let's start with a very simple computer vision algorithm, optical flow. Everyone knows optical flow, okay? Computer vision or image processing 101. How would you do it with an event camera? Let's start with a very simple scene. Let's assume that the event camera is facing a black to white transition that is moving from left to right, okay? So a given pixel of the event camera experiences a change of intensity from white to black. So it's a negative change of intensity. Here we encode negative with black. And you see, in fact, that while the pattern is moving from left to right, you can see that the line is moving from left to right. And what is this here? This is the time of the last event. So the time at which the last event was recorded. What would this information look like in the space-time domain, x, y, and t? Any suggestions? Say ahead. A plane, a ramp. So this is the x and y plane, the space domain, and the vertical one is the time domain. So this line moving in front of the camera basically would trigger a plane of events, okay? Very simple scenario. Optical flow, well, delta x over delta t, done. Okay, I want it to be very simple, but basically you can see how, thanks to the temporal dimension, you have more information in order to make your decisions. Of course, you don't want to do it like this, because otherwise you would be approximating everything with planes. But this to tell you, how could you do it in a very simple way. So, but more in general, how do we process this strange output of an event camera? Well, there are two schools of approaches. There are approaches called event-by-event methods, that what they do is that they incrementally take an event after the other one and compute the output of your computer vision algorithm, whatever algorithm that be. So for every recorded input, there is an updated output. They basically apply the generation model of the event camera that we have just seen. There is a second school of approaches instead called batch methods that, from the name, they batch events over a certain time window, or alternatively, they batch the last n events, and they process them all together. That's the idea, okay? What is the limitation of these approaches? Well, the limitation is that now you are sacrificing a little bit of latency, depending on how many events you need, okay? But they have interesting properties. We're going to look at that. Let's start with event-by-event methods. So let's start with the measurement model of the event camera. I told you that an event is generated when the logarithm of the intensity, the difference of the logarithms of the intensity passes a threshold. Let's call the logarithm just capital L for simplicity. And let's assume that we have a patch, P, that lies on a black to white transition in the 3D world, and that you have the event camera that is moving in front of this patch, okay? The optics of an event camera is exactly the same optics as a standard camera, so the standard projection equations apply. What happens if I move the camera parallel to the edge? Will there be events? Who says no? Who says yes? Excellent, indeed. If I move the event camera parallel to the edge, of course, there should be no events. Maybe you get background noise. What happens if I move the event camera perpendicular to the edge? Well, there will be the maximum generation of events. So it appears clear that the events rate should be proportional to the scalar product between the optical flow, so the direction of motion, and the gradient of the patch. Does it make sense? So in principle, you can take this equation, derive it, then use the optical flow equations. You can do it. And then you end up with this simple formula. So I skipped all the intermediate steps. But this is the first order approximation of the generative event model, so of this one. It says that an event is generated whenever the scalar product between the patch gradient, so which is a vector, so nabla L, call it the gradient of the intensity, and the optical flow in pixels per second passes a threshold. This equation is very interesting because if you know the optical flow, you can derive the gradient and reconstruct the intensity. But if you know the intensity, you can reconstruct the optical flow, which indirectly allows you to do feature tracking or even SLAM, simultaneous localization and mapping, right? What if you don't know any of them? Well, then you do recursive estimation. You assume one known and you measure the other one. Then at the next step, you assume the other one known and you measure the first one. People have done all these flavors. Let me show you some interesting applications of this first order approximation of the event generation model. Here we applied it to extend the very famous Lucas-Canade tracking algorithm. You should know very well Lucas-Canade. Here we extended it to work with events and frames. So we are able to track features in the blind time between two frames. And what we do is applying the first order approximation of the event generation model. So in this case, we want to know U, the optical flow, but we know the intensity. And then many people ask me, can you track features without using frames? Absolutely, yes. We also have made an event-based corner detection algorithm that, for example, mimics the fast corner detector, where now, instead of the intensity, you have the time information. It is completely asynchronous. So you can do everything, both from events or from events and frames. But these feature tracks are very useful, especially in robotics, because as I told you at the very beginning of this talk, in robotics, estimating the robot motion, especially in challenging conditions, is very, very difficult. And especially motion blur is very, very difficult when you increase the agility of a robot. Many people ask me, why are we interested in having agile robots? Because if you want to buy a robot, it should be better than a human, right? So eventually they will have to do the same task as a human, but much faster. So that's why the whole community is super interested in agile robotics. Now, in order to stress test our algorithm, we attach the event camera to its USB cable very, very strongly, and then we spin it as a cowboy. And there is also a standard camera. The standard camera you're going to see in the video is motion blurred, but the event camera is not. Of course, the information is different, but this information is enough to detect features and track them over time. So this is my student, Henri. He's spinning the standard camera and the event camera. You can see the standard camera is so motion blurred, and it experiences such high dynamic changes of illumination that we cannot track features. But with event cameras, we can do it. And we are able to reconstruct the motion of the camera. In the paper, we also compare against the inertial data. We also compare against other cameras and so on. And you can clearly see that there is an added value using event cameras. We showed that for state estimation, so motion estimation, event camera improves performance by up to 85%. And indeed, we use it on drones. So we call this algorithm ultimate SLAM, because we wanted to provoke a little bit the SLAM community. In robotics, the community of SLAM is the one that is interested in simultaneous localization and mapping. So we wanted to tell them, look, if you add an event camera to your suite of sensors, you can actually make it much better. So we called it ultimate SLAM. So in this video that you're going to see, there is a drone that is autonomous. And it's just following a circular trajectory over and over again. And on the left, you're going to see standard frames from a standard camera. And in the middle, you're going to see events from the event camera. As you can see, I turned off the light, and you can see that the drone was not affected by the motion blur. Because what happens when you turn off the light? Then now the standard camera will increase the exposure time in order to gather more information, but it won't manage because it's so motion blurred that you can't see anything. While with the event camera, actually, we do not experience that, and we can detect features, track them, and use them for motion estimation. A drone can only fly if it can estimate its own motion, so we were able to do it. We took this even further, and we addressed a very important problem in robotics. Now that drones are becoming very, very popular, only in Switzerland, there were more than 10,000 autonomous flights in Bern, Lugano, and Zurich between two hospitals since 2017 until today, and there are still drones flying every day in Zurich, autonomously. However, in Zurich, there were two crashes caused by, one crash was caused by a motor failure. What happens when a motor fails? Well, if you have a quadcopter drone with three propellers, you're going to experience this spinning effect. So because of the principle of conservation of the angular momentum, so now you have an asymmetric configuration, basically the drone is going to spin like a ballerina. Then what happens? Well, you can do unstable hovering. So people have shown 10 years ago that if you have GPS, you have the estimate of the position, and while the drone continues spinning, you can remain on the spot, spinning on the spot. So you save it. If you don't have position reference, the drone, while spinning, will drift away and eventually crash. We tried to do it with standard cameras, but then there was a breaking point when the illumination is too low because there is motion blur. But with the event camera, it's not a problem, right? Because in principle, there is no motion blur. So here, you're going to see already the drone spinning because we induced the failure of one motor. Now you're going to see what the video feed looks like. This is the standard frames. And this is the events, and the raw events. You see? We can detect features from the standard frames, but because they are motion blur, the features are concentrated in the middle of the image, where the motion blur is ideally 0. But with the event camera, we can detect features all uniformly around the image and allow both hovering and trajectory following, controlled trajectory following. So you see the drone is spinning, but while spinning, we can control it to follow a given trajectory. It's a straight trajectory, back and forth. So we also open sourced this code because we thought this could help companies, if they want to implement it, to make their drones safer. Here you see what happens if you lower the illumination in the office. The standard camera has a failure point at 50 lux. Now you see with 50 lux, with the standard camera on the left, the drone crashes. Well, actually, it drifted, and then it crashed into the wall. While with the event camera, we can go down to illuminations of 10 lux. Okay? This actually triggered the interest of NASA, also gave us a prize, and then we started a multi-year collaboration with the NASA JPL. We published a few papers, and one of them is about exploring the use of event cameras for the next Mars mission, which is planned for 2030. They want to enter lava tubes. These are lava tubes not on Mars, but rather on the Moon and on the Earth. And during the entrance maneuver, there will be a lot of dynamic changes of illumination. That's where event cameras might actually help. So we did some tests on a cave next to JPL, and we saw indeed that this would help. So they are considering it among many other sensors. Okay, so what we have seen so far is the first lines of approaches. So approaches that basically process events by events, one after the other one. But now let's look at the batch methods that can provide an even more robust estimate, but sacrificing a little bit of latency. Still, the latency is much less than you would have with a standard camera, by the way. How do these batch methods work? Well, actually now, interestingly, they all converged to a school of approaches called the contrast maximization. By the way, if you're interested in all these approaches, there is a survey paper that we published a few years ago with all the event camera people in the world. What is the idea? So I'm going to show you two videos simultaneously. Focus first on the one on the left. If I ask you, what scene generated this cloud of events, you wouldn't know what the answer is. By the way, here you see X and Y, and this dimension is the time. So this is around 5 milliseconds of events. It can be a lot, depending on the dynamics of the scene, how fast the camera moved. But now, this pattern of events depends on the type of motion and the underlying scene. Interestingly, for many types of motion, you can do an undistortion. Check carefully. Let me explain it intuitively. If there was a pure rotation, you could unrotate all the events, and then you would see a sharp image, right? But actually, you can do it also for non-pure rotations. For example, for homographic motions. In fact, many scenes can be approximated as a translation or rotation in front of a plane, rototranslation in front of a distant plane. So in principle, you can apply it to almost any other problem. What is the underlying algorithm here? Here, we are distorting the events in the temporal dimension in order to look at them from the direction of motion that generated them. So if you have a parametric function of the motion trajectory, we are going to solve an optimization method that looks via gradient descent for the parameters of that parametric function. How do we do it? We need to define the objective function. Well, at each iteration, we project this point cloud onto a plane by accumulating events. When you accumulate events, you count them, and then you get a grayscale image. Now look at the right video. Basically, but through this undistortion, you're going to make the reconstructed image sharper and sharper. Is it clear? We don't call this a reconstructed image. We call it integrated event image, because it's totally different than pure reconstruction. So what is now the underlying algorithm? Is the following. At each iteration, so we have a feedback loop, where at each iteration, we take the events, we work them in the time dimension. We try to maximize the focus of the resulting image, which is the same as autofocus algorithm. So typically, you maximize the variance of the resulting image. And you do this until you reach a certain sharpness level. That's the idea, okay? And we applied this to many problems. Here you see video stabilization. You know, video stabilization is a long-studied problem, but typically it uses IMUs or standard cameras, so the update rate is very slow. Here we are actually using the events. So we accumulate events over tiny time windows, or actually here we process a constant number of events. And then we use this contrast maximization algorithm to motion compensate the images. In this case, if it was a pure trade-off rotational motion. And then we render, rectified event images. This actually triggered the interest of many smartphone companies, including Huawei and others, because many people want to take pictures of the moon at night. But the problem is that you have the handshaking of the hand. With the IMU, you cannot help, but with the event camera, you can possibly help. So that we consulted them to actually make this possible. Let me show you another application of this contrast maximization framework, motion segmentation. Here there are 3 underlying patterns, but each one with its own motion parameterization. So in this case, what we needed to do is to apply this optimization 3 times, as many as the number of classes of objects that we wanted to segment: the cyclist, the pedestrian, and the background motion. Here, the event camera was attached to a car that was driving in Zurich. So here you can see the pedestrian, here you can see the cyclist, and here the background motion. This is to tell you that actually it doesn't only work with rotation, it can work with any general motion, okay, within certain assumptions. Why is this algorithm useful? It can be useful because, for example, you can use it to do self-supervised learning with event cameras. You can, for example, use as a loss function this contrast maximization framework. And many people ask me, okay, but what if you don't know to which object class each event belongs to? Yeah, indeed. That's a very important problem. So typically what we do is a soft data association, probabilistic data association. So while we solve this optimization problem, we also assign an event to a given class, and then we define this at the next iteration. We also applied this contrast maximization framework to a robotic problem, safety. We use the drone because drones are super agile. Here, what are we doing? Here we are throwing objects to the drone, and the drone is dodging the object. How does it work? We use this contrast maximization framework. So on the right, you see the space-time volume of events, and this shadow here is the trace of events left by the ball. Now let's look in more detail. You know, with an event camera, you have microsecond resolution, so you can zoom in the time dimension. Now the ball becomes very clear. You can clearly see that the ball events have a different temporal statistics than the events associated to the ego motion, so to the ones that belong to the stationary background, which are only triggered by the ego motion of the robot. So you can apply very simple statistical methods to tell apart events generated by the self-motion of the ball from events generated by the ego motion of the vehicle, because they belong to the stationary background, okay? Can you do this with a standard camera? I mean, not specifically apply this algorithm, but can you achieve the same demonstration with a standard camera? Who says yes? Who says no? Of course you can. Why not? I mean, it would be a different algorithm. What prevents you from doing it? Nothing. But look at which latency we achieved, 3.5 milliseconds. To achieve the same with a standard camera, you need around 300 frames per second. So now what do you pay? Bandwidth. You're going to have to process those almost 300 frames per second in real time. And look what processor we used. I didn't write it there. We used actually a simple CPU, actually an Odroid CPU, which is an ARM processor, very old one at the time. So that means that you don't need, in principle, sophisticated computers to do it, because now you have a much lower bandwidth, and you can process these things also on very computational cheap processors. Okay? That's the message I would like to convey. We also apply this problem to catching balls. Now, from a scientific point of view, we reverted the policy. Instead of dodging them, you catch them. It wasn't so simple. It took 1 year to do it. But to tell the story, it's easier to say that. But the underlying vision algorithm is the same. We detect the ball like in the other algorithm by telling apart events that belong to the ball from events that belong to the stationary background. And here then we trained the controller with reinforcement learning, because it would be very difficult with standard controllers. But again, we achieved the same latency. So again, thanks to the event camera, we were able to do this at impressive speeds without sacrificing bandwidth. Let me show you another thing. Now, an industrial application, inspection. This is actually, one of the main applications of robotics is inspection of everything. Inspection of our falling apart infrastructure, as well as inspection, of course, of airplanes. At Boeing, for example, they inspect wings every time they build them. And one thing that you're going to see here is the inspection of the holes where you're going to fix the wing on the airplane. So basically, This is a mock-up wing, of course. It's just a bar with multiple holes. But this was done by Boeing in collaboration with Strata from Abu Dhabi, where they actually manufacture the wing. There are many holes here. These holes are called, by the way, countersinks. I didn't even know. So they need to measure the diameter and depth of each hole to make sure that it stays within the tolerance before shipping it. Typically, the inspection works by putting a camera on the end effector and stopping the camera in front of each hole. You see? Stop and go motion. Pause on each hole. Take a picture, analyze it. 1 second per hole. With the event camera, you don't need to stop. One swipe, done. So this is to tell you basically the potential that the event cameras offer. By the way, how did they then measure the diameter and depth of the holes? Using the contrast maximization algorithm I just told you. Because in the event stream, you will see a pattern of circles in space and time. So they look like a slanted cylinder. And then you undistort it, and it looks like a perfect cylinder. And then you have a lot of information to measure actually your diameters and depth. Okay? They also published a paper last year. So this has tremendous potential for inspection, in my opinion. But now let's look at the future. For the past 10 years, because event cameras became commercially available in 2014, that's why I say 10 years. For the past 10 years, researchers looked mostly at event cameras alone. Why? Well, it's obvious, because they wanted to understand and characterize the event camera and see what the potential is. But now, we go back to what I told you at the beginning. There is not much you can actually possibly do with an event camera alone. The best is to combine it with a standard camera, because an event camera is a high-pass filter, and the standard camera is a low-pass filter. So with both, you cover kind of a lot of the frequency spectrum. So here you see a way to combine an event camera with a standard camera. There are multiple ways. You can also share the same pixels, or you can put a beam splitter. But this is an easy way. You put the event camera and the RGB camera side by side. So you get frames at constant time intervals. You can also modulate the frame rate in order to lower the bandwidth. By the way, we are working with Meta, actually exactly on this problem, trying to lower the energy by reducing the frame rate of the camera for AR/VR applications. And then you have the events continuously in time, in the blind time between two frames. Now the problem is, how do you unlock all what has been done on deep learning over the past years to event cameras? That's a big question. How do you apply basic neural networks to event cameras? So there are 3 schools of approaches. We are only going to see the first 2, and then we can talk about the third one in the question session if you want. The most naive way that actually covers 99% of the papers on event cameras consists of using the standard synchronous artificial neural network designed for standard images. You convert the events into something that looks like a frame, and then you apply standard computer vision algorithms. But you need to retrain them on this new type of event data. The second line of approaches, which you're going to see in a moment, is asynchronous sparse neural networks. So now we can modify standard CNNs or GNNs to make them work asynchronously. Beautiful, but the hardware still doesn't exist unless you implement them with an FPGA or ASIC in the future. The third line of approaches is to use spanning neural networks. They are spatio-temporally asynchronous in space and time, and the hardware exists. The problem is that there is a sim-to-real gap. So at the moment, these networks are not really differentiable. So when you do the training, then they are not really emulating the real working principle on hardware. So when you transfer them to the real world, they don't maintain the same performance. But that research community is making tremendous progress. We're going to talk about the first 2 here. How do we apply standard neural networks to event cameras? The key idea is the following. This is the stream of events in space and time. You can convert this stream of events into a voxel grid representation in space and time, where now you discretize x, y, and t in voxels, and for each voxels, you count the number of positive or negative events. So these are, you can call them tensors, okay? Because they also have the time dimension. Now, from the perspective of the neural network, these look like basically frames, a very high frame rate, but different now because they are binary. But you can do amazing things even with just this simple voxel grid representation. For example, this is a paper we published in CVPR21 and 22 called Time Lens. We are doing video frame interpolation or slow motion video. We take as input to the network a 20 FPS video, or in general, a very low frame rate video, the events between the frames, and we are able to reconstruct, to interpolate frames at a much higher temporal resolution. We can go up to an upscaling factor of 50. So you see again, the input video is choppy, but the input events are continuous in time, and then the reconstructed video is much smoother. Why? Because we are borrowing information from both the standard frame and from the events. Why? Why are we doing this? Well, let's read what I wrote here. We can get an upsampling factor of 50, but what is actually very interesting is the second part, with only 1/40 of the memory footprint. So if you ever recorded the slow motion videos, you know that they're actually very, very short videos. They only last less than a few seconds, typically. And if you want to record them minutes or hours, well, then you need special hardware and also a very, very large SD card. Here, we can basically record a very long video with 1/40 of the memory footprint. That means you can record a 40 times longer video. That's the idea. So, for example, 40 minutes of video instead of 1 minute. This triggered a lot of interest of smartphone companies who are trying to put it on smartphones nowadays. Let me show you another video of this paper. Input video is on the left at 28 FPS, and output video at 310 FPS on the right. So here, in a scaling factor of 10. Notice how the output video is much smoother. How does it work? We have an attention network that basically decides from which sensory data to use the information to compute optic flow, because the underlying algorithm uses optical flow after all. So you can compute optic flow from RGB patches or from the events. And the attention network basically decides from which of these two sensor data to use in order to compute the optic flow. The best one is this one. Actually, this is a Timelines++, which we published in CVPR 2022. The code is open source, by the way. I show you this one. It's very cool. So the input was at 100 FPS video, and this is now the output at 5,000 FPS. First in real time and now in slow motion. So here we are borrowing the information of the color and the absolute intensity from the last frame, actually from the two opposite frames, from the last and the next frame, and then we use the events in between. Also, I forgot to say, the spatial resolution of the standard camera here is much larger than the spatial resolution of the event camera. So there is also, you know, a scaling also there. Company Prophecy, which is the largest event camera company based in Paris, they modified our algorithm to actually do deep blurring. Let me show it again. So here is a tennis player. This is the standard frames that are motion blurred, and this is the corresponding events. And now you're going to see how they're going to deep blur the standard image. There you go. So they're trying to port this to smartphones now. So they're using this neural network. Can you do it without neural network? Of course. Without a neural network, with model-based approaches, basically, you know how do you deblur a standard frame? By subtracting to the blurry frame the double integral of the events. There was a paper, CVPR 2019, by Richard Hartley about that. OK, so the approaches I just showed you basically voxelize the event stream in order to apply standard computer vision, standard neural networks developed for standard images. But in principle, you don't need to do it. You can actually make CNNs and even GNNs asynchronous. And I want to show you, motivate this with a very, very sensitive topic, advanced driver assistance systems. As I told you, we are still very far from level 5 autonomy. I mean, Tesla is one of the best autopilots, and it's not autonomous, right? It's level 3. This is a random video from YouTube. They use multiple cameras looking at the sides and at the front. And they have, you know, an excellent a detection of all the cars and other traffic participants. But there is a problem in automotive. Basically, so on the x-axis you have the ears, and on the left you see the bandwidth. At the moment we are here, level 3 autonomy, and this is the kind of bandwidth in gigabits per second. So at the moment we spend around 200 gigabits per second. As we increase the autonomy levels of these systems towards level 5, we are going to increase more and more the data bandwidth and also the memory footprint as well. So can we do better? Many people are working on this problem. So we started tackling this problem with event cameras. This is what the output of the event camera looks like when you're driving. You see only the scenes, only the objects that are moving, or the pixels that correspond on edges trigger events. But this information is sparser than you would have with a standard image. So in a paper we published last month, here we tackled the problem of inter-frame object detection. So can we detect traffic participants like pedestrians, cars, cyclists, much faster than we can do with a standard camera? At the moment, the state-of-the-art ADAS system is from Mobileye, and it has a frame rate of 30 Hertz. And they need 3 images to make a decision about whether there is a pedestrian or not. That means a 100 milliseconds latency. Here we show we can do it at the latency of 0.2 milliseconds. So that's the illustration. Can we do it even before the next frame arrives? So we call this inter-frame object detection. And the idea is to mix frames and events. This is actually motivated by the visual cortex, our visual cortex. So as you know, we have rods and cones in our brain, in our eyes. Some are sensitive to color, but they are very slow. They have a slow reaction time. Other ones are instead only sensitive to intensity. They are very good in low light. They have a very fast reaction time. But that's not just it. We also have different pathways, magno and parvo pathways in our brain, that also have different reaction times. We can call them a slow-fast network in our brain. So basically, a pathway reacts to very fast movements, and the other pathway actually is cognitive and is very slow. Motivated by this, we proposed a slow-fast architecture, or hybrid asynchronous object detection architecture, where we have 2 layers of cognition, a fast cognitive layer and a slow cognitive layer. The fast cognitive layer takes information from the event camera, but at the same time, why not, using contextual information from the standard camera when this becomes available. If it's not available, doesn't mind it. You only use the event camera. And then produce control commands at the resolution of the single events, using the information of both the event camera and the standard camera, or just one of the sensors. How do we translate this in practice? So now the fast layer, for us, is an asynchronous graph neural network, and the slow cognitive layer is a CNN. The CNN operates on images and shares some embedding with the asynchronous GNN that takes both this embedding as input as well as raw events. So the slow layer, operated by the CNN, can produce object detections at low frame rate. And the event camera instead is used to give fast update rates. Okay, I hope the illustration is clear. How do we do it? Okay, so remember the space-time volume of events. So this is the last frame, RGB. This is the last frame, and these are the space-time events since the last frame. We transform them into a graph of nearby events. You see here what the graph looks like if you zoom in enough. Now the idea is to modify the graph neural network such that we can update the individual nodes at the resolution of the single events. So only the nodes that are affected by new measurement are being updated, and so do they to the ones that are connected to them. The problem? Well, the hardware at the moment is synchronous. So at the moment, this is only showcased on, on our synchronous machines. But the potential is very high. Already there is a group in Delft that has implemented this asynchronous graph neural network on an FPGA. And they plan to put it on an ASICs. That's where basically you will really show the clear potential of these things. What is the update rate that we achieved in this paper? Well, we showed that if you use just a standard 20 FPS camera plus an event camera, you can achieve the same latency as a 5000 FPS camera, so 0.2 milliseconds, with a bandwidth of a 50 FPS camera without compromising accuracy. So by combining event camera with a standard camera, you basically lower the latency by 100 times as well as the bandwidth. So now you have a 0.2 milliseconds latency. Many people ask me, do you even need it? The point is, in all this automotive industry, you want to have as many samples as possible in order to make more informed decisions. As I was telling you, with frame-based camera, they need 3 frames, because otherwise then the latency is too high. But with event cameras, now you have 0.2 milliseconds. You can take more, of course, in order to make more informed decisions. That's the idea. It still gives you an advantage. You can actually detect pedestrians even before they become visible from the standard frame. If you're interested, I can show you a lot of stuff in the question session. This is the concluding slide. So event cameras now are 10-year-old commercially. They were first prototypized at the Institute of Neuroinformatics by Professor Delbruck. The resolution in 2008 was 128 by 128 pixels. So as you can see, the pixels were very large. Only in 2014, they commercialized the sensor. So at the moment, the sensor is 10 years old, in fact. In 2019, Apple and Meta published, only Apple published more than 100 patents on event cameras, mostly on eye tracking, while Facebook tried to reinvent the event camera. There is an interesting patent by Richard Newcomb, by the way, if you know him. In 2021, the 3 of the largest standard camera manufacturers, Sony, Samsung, and Omnivision, entered the game of event vision. They started injecting a lot of money, billions, and thanks to their money, they were able to miniaturize the pixel from 40 microns to 5 microns. Now it's around 3 microns, and reach resolution of full HD. So the best is yet to come, I would say. Meta opened the Neuromorphic Sensing Lab in 2022. ESA sent already 3 event cameras in space. The first time was in 2022, the last one a few weeks ago. There are 2 on the space station and 1 on a CUBE satellite. And then camera manufacturer, event camera company, Prophecy and Qualcomm signed a multi-year deal to put their sensors on smartphones. On the academic side, the event camera is gaining a lot of interest. To be honest, in the last 5 years, event cameras have won a Best Paper Award or Best Paper Award finalist at the main Vision conference, so it's bringing a lot of luck. I guess they are interesting to the community. And with this, I would like to thank you for your attention and take questions if you're interested.
We have time for a few questions.
Now you're doing it again. Sorry, I'm supposed to wait for the microphone. You mentioned at the beginning of the talk that you were getting out of autonomous cars and getting into UAVs because it was getting crowded, but now you're back into it. Why the change?
I'm glad you were listening very carefully. Indeed, well, you see, you can always be wrong, right? I think, well, I mean, now we understand what the key problems are. Okay, at the beginning, it was mostly trying to get the things developed in mobile robotics like SLAM and some scene understanding, planning algorithms into the wild. And now we understand that actually, we are tremendously far away from human performance. Just because we are 99% doesn't mean that we are there. We need to achieve, as you know, 99 points followed by another 29s after the decimal point. So, and this is a big research problem that is actually taking a lot of the computer vision, research.
Thanks for the talk. For machine vision application, comparing to conventional camera, do you see any limitation or disadvantage other than not having like the absolute intensity? for event-based camera?
So the question is if there is any disadvantage for standard RGB cameras? Is that the question?
Yes, for machine vision.
No, I don't see any advantage. I mean, as a roboticist, I always advocate that the best is redundancy, so you should use as many sensors as possible. For autonomous driving, for example, or automotive vision in general, there are also LiDAR, there are also radars, of course, in order to be able to see at night with snow, with fog and rain. So the more sensors and the more complementary they are, the better they are, right? Also thermal cameras, night vision sensors as well. So I wouldn't say that, the standard cameras will ever go away. Actually, no, absolutely not. I mean, the research is improving there, they're improving the dynamic range, and so on. So, no.
Hello. So you mentioned that you have been combining the event camera with the conventional camera. So I'm wondering that if there are any specific design camera that just work in between the event camera and the conventional camera?
Yes, there are. There are, indeed. So nowadays, the state-of-the-art that was published only a few months ago by Sony and OmniVision is an hybrid sensor that interleaves event pixels with RGB pixels. So there is an R, G, and a B blue pixel, and then an event pixel. So 1 every 4 is an event pixel. This is also, again, mimicking kind of the arrangement, well, very loosely, of our cones and rods in our eyes, by the way, okay? But so that's the idea. Because in the end, events, you don't need them the high spatial resolution. Also because if you have too much of a spatial resolution, then maybe the bandwidth is going to become also quite large. But they are fast. So you don't need a high spatial resolution, but rather high temporal resolution, okay?
Yeah. Sure, thank you.
So I had a question as well.
Mm-hmm.
So you talked a lot about event cameras, especially when it comes to agile applications. What specifications, like in the event camera, would you like improved over time so that your needs are better set?
Very good question. So what would I improve of event cameras? At the moment, event cameras have the following limitation: the fill factor. So the first event camera had a fill factor of 20%. Why? What is the fill factor? It's basically the ratio of exposed region with respect to the entire area of the pixel. So the majority of the pixel area was actually occupied by the electronics. But that was because it was born in academic research labs, and you need a lot of money to make to overcome the problem. So then Sony, OmniVision, and Samsung, basically they used BSI technology, and now the fill factor is very large, almost as large as that of a standard camera. The problem is still, you need a lot of transistors. You need 11 transistors instead of just 1. Okay, that's a problem. Then another thing is the refractory period. So event cameras need a time in order to reset the voltage after the last event, and that time at the moment is small but not completely negligible. If you could reduce the refractory period, then you can make them even faster reaction time. CERN, the particle accelerator here in Geneva, is very interested in that. They're actually interested in building a gigahertz possible event camera for neutrino detection, for new portable neutrino detectors, they say. And they asked for an array of super fast event cameras. By the way, the event camera was inspired by the CERN Large Hadron Collider because, this big thing actually behaves as an event camera. And one of the authors of that paper of event cameras from 2008 was actually working at CERN.
Any other questions?
Yes. Hi. So in your system, you describe an asynchronous image sensor, which is connected to a system which is based on synchronous computing. And you mentioned in one of your slides that you had to use FPGA to make the GNN run in a way that is at the same asynchronous rate as the input sensor. So my question is, at what point do you think that your systems will be bottlenecked by the synchronous nature of today's computing devices? And how far do you want asynchronous behavior to be pushed down into the computing stack so that more and more of the system becomes asynchronous rather than tied to, say, a periodic clock rate?
Okay, honestly, I didn't clearly understood the entire question, but if we can continue after offline, but if I understand how much do you want asynchronous behavior, indeed, I mean, I guess there is, okay, we are not working now on the effective implementation of the FPGA because we are not FPGA people, So I don't know what here the latency is, but they are really saying that they have really a response time that is almost instantaneous. Although I can, in the paper by Charlotte Frankel from TU Delft, she claims in the paper a 16 microsecond latency per each event. But this is done on a 128 by 128 event camera, okay? So now scaling that up, that could actually increase. Now, the second question is, how much do you really require this asynchronous behavior? It's a very good question. I think that there are many applications that we cannot even think for now, you know, what they could be. At the moment, there is a lot of intellectual interest in event cameras to also reverse engineer our brain, okay? So a lot of this research comes from the Institute of Neuroinformatics of UCH. But I think that, you see, now more and more people are coming up with the applications that before we didn't think they were actually important. However, for example, I showed you at the very beginning these super agile drones that are outperforming human pilots. Birds are even more agile. And the reason why they're more agile is because they fly sitting on the aircraft. So they're measuring basically events one after the other one, not through the goggles that receive frames from a standard camera. So having said that, that means that you can actually make now these vehicles very, very agile. Okay? That's for them a possible application.
With that, let's thank Professor Scaramuzza.
Thank you.